A very good evening, ladies and gentlemen. Hope you are safe and doing well.
The key is to join an industry which you have a passion for. With that passion, knowing what you are up to and your specific role lead you towards a success.
I am Isuri Mayadunne.
I'm Amaya Silva. We will be your hosts for today.
We are delighted to have you all here today with the orientation program of our very first project. It's all about BME, the workshop series on MRI, magnetic resonance imaging. This workshop series caters to biomedical engineers, medical technology professionals, and undergraduates. Thank you for registering and joining with us for the orientation.
Without taking much time, I would now like to invite the program lead of Y2NPro, Mr. Iroshan Ratnayakar, to welcome today's gathering. He was an undergraduate student on Bachelor of Technology in Electrical Engineering of Open University of Sri Lanka, and he is currently an ELV trainee at Hales Fentons. He is an active volunteer of IEEE Sri Lanka section and was the former chairman of IEEE student branch of the Open University. He was also the former co-chair and program lead of IEEE Techno Meetup Sri Lanka. He is currently volunteering as a member of IEEE Sri Lanka section Student Activities Committee 2. Mr. Iroshan, over to you.
Thank you, Maya and Isuri. Hope I am audible to you.
Yes, you are.
A very good evening to you all of you. Today, on behalf of Y2NPro family, I welcome you all to the freshers evening. This evening marks the orientation session of our workshop series on the magnetic resonance imaging in biomedical engineering. As you all already know, Young to Niche Professional is a new initiative of the IEEE Young Professional Sri Lanka that will focus on providing the request experience to the niche communities in the different industrial field and enhancing their knowledge in the respective areas. Y2NPro programs enable a platform for young industrial learners to enhance their knowledge and get more experience, especially in the niche technologies by learning from the expertise in the industry. Also, we're glad to honor to announce that we are partnered with the EMB Global and the Sri Lanka chapters. Today comes the beginning of the series of the workshop, which will serve as an introduction to the next course for the young interested industrial community. We focus on basic of biomedical engineering, medical techniques during the orientation session. It's my honor to welcome the guest speaker, Mr. Kanchana Wijesinghe, to commence this milestone. Last but not last, warm I welcome to all the young professionals who gathered with us today. This is beginning of the becoming an expert. Thank you.
Thank you very much, Mr. Iroshan, for welcoming the audience. Now, we are about to head on to the awareness session of IEEE EMBS Sri Lanka chapter. Do you all know what EMBS stands for? EMBS stands for Engineering in Medicine and Biology Society. IEEE EMBS is the world's largest international society of biomedical engineers. It has 12,000 individuals in 97 countries all over the world. EMBS gives its members access to the people, practices, instructions, ideas, and opinions that shape one of the fastest growing fields in science. Today, you all are getting a valuable chance to learn and join IEEE EMBS Sri Lanka chapter. To make you all aware of EMBS, we have a very special person. Isn't it, Amaya?
Obviously, he is none other than the Vice Chairman of IEEE EMBS Sri Lanka chapter, Dr. Ruwan Ranavira. He earned his Bachelor of Science in Electrical and Electronic Engineering from the University of Peradeniya and his Master's in Biomedical Engineering at Purdue University, USA. He holds his PhD from the School of Electrical and Computer Engineering at Purdue University, USA. He was the chairman of IEEE Sri Lanka section in 2015 and inspired IEEEans through his knowledge and experience. Dr. Ruwan, the spotlight is yours.
Thank you, Amaya and Nisuri, for that nice introduction. My task here today is basically introducing EMBS, or Engineering in Medicine and Biology Society, to the audience, and trying to convince you guys that it may be beneficial for you guys to actually join this society. So let me share my PowerPoint with you. I'm not sure whether I have. Can you guys see my screen?
Yes, sir. We can.
Okay,
Yes,
thank
sir,
you.
this is Ibrahim.
Right, and I might also have to make the sounds shareable. So let me see how it's working. Share my audio. Then original optimize. No, we'll see. As it comes to the video, we'll try to. Okay, without taking much time, let me go to the presentation. I'm going to talk about what EMBS is, right? As Isuri has, actually gone through it. It basically, Engineering in Medicine and Biology Society is the largest international society of biomedical engineers in the world, the whole world, with over 12,000 members spread around across 97 countries, right? So the society members have access to people of similar interest, like biomedical engineers, also the practices through standards, as well as many other information, ideas, literature, and perspectives influencing one of science's fastest expanding fields. And someone. All right. So, okay. So thank you, host, for unmuting the others. So basically, EMBS is basically revolutionizing the future of medicine and healthcare by working together. Now, this is basically not just engineers, not just medical professionals. It's a full, complete mix of everyone. So, right. So you will see that people who are practicing EMBS or biomedical engineering, basically, biomedical engineers. They come from various fields, engineering, medicine, physics, chemistry, and all these pieces. So all these are coming together to improve the lives of people, right? So the EMBS of this is the mission statement of IEEE EMBS, the engineering in the EMBS society, EMB society of IEEE advances the application of engineering sciences and technology to medicine and biology. So applying engineering to medicine and biology promotes the profession and provides global leadership for the benefit of its members and humanity by disseminating knowledge, setting standard, fostering professional development, and recognizing excellence. Right? This is the mission statement, and the research and application. So basically, this is the definition of biomedical engineering, right? Research and application of engineering concepts and methodologies to biology, medicine, and health sciences. That is biomedical engineering, to give effective solutions to issues and problems in biological, medical, and healthcare challenges. Is an area of interest for the EMBS members, right? So that's the goal. And mathematical theories, physical, biological, and chemical concepts, computer models and algorithms, and all these other things that we use as engineers, we will be using to solve problems in these other domains, biology, medical field, as well as healthcare fields, right? The professionals who work in these areas are trained for different purpose. We as engineers are trained for solving problems using mathematics, physics, and chemistry, and things like basic sciences. So this is basically what biomedical engineers do, and this EMBS society, EMB society, basically gives us a platform to gather together and put our efforts together and collaborate to solve such problems. Okay, so it's a very multidisciplinary field, as you all know. So some of the things that biomedical engineers do are basically designing diagnostic systems, like, for example, MRIs, CTs, and all sorts of other diagnostic systems, ultrasound. All these medical imaging systems, medical equipment are designed by biomedical engineers. And therapeutic systems, like, for example, surgical systems and things like that, they are designed by biomedical engineers. Healthcare and bioinformation systems to handle, now these days a lot of information is being generated everywhere. So we use these informations, biomedical engineers use these informations to model phenomena around us and also predict things, so that we can prevent and mitigate certain things, like, for example, spread of COVID, right? And also many other technologies and methodologies are developed by the engineers, right? So if you talk about the global reach, we have 125 EMBS chapters around the world, with 30 joint chapters and 194 student branch chapters, including few in Sri Lanka. And also we have 86 student clubs. And when it comes to Sri Lanka, in addition to the couple of EMBS societies, student chapters we have, and the student members that we have 12 full members, EMBS full members in Sri Lanka. And this is not a good enough number. We need this number improved. So therefore, I invite you to join the EMBS society, and we'll try to help you gain some valuable insight into what you can gain from joining this, right? So let me, so I have listed some of the benefits that students and other professionals can get from joining the EMBS. Students as well as, undergraduate as well as postgraduate students, some of you may be postgraduate students, join, you get support for your projects, monetary as well as other means, assistance with formation of student chapters, access to publications. This is one of the biggest things that you get. The Pulse magazine and many other EMBS transactions and things like that, right? Journal publications, conference publications, and things like that related to EMBS. Student paper competitions, some opportunities for you guys. Student events at conferences, which gives you some networking, chances. Summer schools to learn about new topics. DLP program, so you can invite some, eminent people in the field to deliver lectures. Networking opportunities and conferences, job opportunities and conferences through these networks, as well as reduced rates in many of the conferences and journals. Now, if you take my experience, I became an IEEE member way back in 2004, just for this purpose, right? You get a huge discount, something like several sometimes few $100s worth of discounts for being a member, right? So this is if you are planning to publish, it's always good to be a member of IEEE as well as these societies, these chapters, right? So let me go into a brief video. This is not a real brief video. It goes for about 12 minutes. Hopefully, I will not run over my 15 minutes. But Amaya, please feel free to stop me if I go over the time. Okay, I won't be upset if you do that. I'm right at 15 minutes. Let me know if you guys can hear. Can you guys hear the sound?
Sound is not available, sir.
Okay, let me see. This is what I use. Yeah, okay, it's there, right? Okay, let me know if it works now.
Most interesting
Yes,
field.
sir.
Good.
Biomedical engineers try to address all kinds of, I think, exciting questions at the interface of medicine and engineering.
I think I've always been fascinated with the brain and how it works.
One of my best friends became paralyzed when we were 13, and I really wanted to help him walk again.
For me, being a mechanical engineer, the heart was the most similar organ to a pump.
You don't have to be a medical doctor to help save lives.
Biomedical engineering brings these two big fields of medicine and engineering together.
It's a very broad field.
It's the field in engineering that really allows you to make an impact in a very perceivable way when it comes to human life.
Imagine a neurologist 30 years ago without imaging. Their options were very limited. And that's a remarkable example of how engineering can impact medicine very dramatically.
We can think, we can feel, we understand, we interact with others. But on the other hand, we know very little about how brain works. In the field of neuroengineering, we focus on non-invasive brain-computer interface. We put electro sensor on the scalp, and this sensor can pick up extremely weak electrical signal generated by the neurons.
We're able to pick up voltage differences in different areas of the scalp. So when a subject imagines using an arm or a leg, it actually activates the motor cortex in much the same way it would activate if they were actually doing that thing in real life.
And then we decode the signal to try to find out what the subject is thinking or intend to do, and then use that signal to control a device.
The promise of research like this is to allow for paralyzed individuals to interact and to communicate again with the outside world.
We do research in the area of wireless sensors and robotics for rehabilitation. Unfortunately, about 50% of the people that you do any sort of rehab with don't get better, and we really don't understand why.
A major question that we're trying to address is whether through the interaction with a robot a person can actually learn motor tasks. that's essential in stroke survivors and traumatic brain injury survivors.
The Lokomat is a robotic exoskeleton for robotic gait training.
Make you walk a little bit faster now, okay?
Manual gait training, as was usually done, was really strenuous on therapists where they had to independently move the person's legs through the standard walking
I
pattern.
want you to think about pulling your knee up nice and high, then you're taking a big giant step.
We've formed a collaboration with the company that develops the Lokomat, and so we're actually able to tap in using our own software and change the way that the robot works.
The motion analysis laboratory was established to perform clinical evaluations, mostly in children with cerebral palsy.
We have 8 infrared cameras that go around the room and they point in the central walkway. The cameras emit the light that gets reflected from the markers, and the computer can pick up the movement of the markers. The green lines show the different bony segments, while the yellow line represents the force that is exerted during gait. It's something that will help the doctors in seeing how the outcome of surgeries or intervention lasts through the time. A lot of times when they come in, they want to impress the clinician, so they tend to walk better than what they would do when they're at home.
The shoe that we have developed has sensors that are embedded in the sole of the shoe itself.
Once they put the shoe on, it's like wearing a normal sneaker. You can have monitoring that is less obtrusive, and it's conducted in their home environment, so we can actually collect more data and have a better insight on how the disease progresses.
Wearable technology has become possible over the past 10 years because of major developments that allow us to integrate sensors into garments.
We have the potential that if you can wear some form of a monitoring device, that your vitals can be monitored on a more regular basis, and we can send that information through a cloud environment before you need to go into an emergency department because you're very unwell.
My father is actually an amputee, and when I was young I promised him I'd make him an arm one day. An amputee can live their life pretty normally with a prosthetic, but the idea that you can just take it to that next level, that's important to me.
One way to do it that we've developed is you could take a plastic scaffold, a polymer scaffold, that could be whatever shape you want, depending on the organ or tissue you're trying to make. Then you might put certain cells on it and give it the right nutrients and also the right mechanical forces, grow it to a certain point, and then do a transplant that onto the patient or into the patient.
If you think about how complex the organ is, it's really difficult to mimic what happens in nature. One of the big challenges is the vascularization. Also, in terms of stem cells, there are a long way to go. We have to understand what makes them differentiate. How can we control them so that they will not develop cancer?
We're working on making various tissues and organs in the body. I mean, new spinal cords, vocal cords, new intestine, heart tissue. So there's a whole range of things that we've been working on. How are the microbubbles doing? Today, in the area of drug delivery, some of the things we're most excited about are nanotechnology, where one might be able to deliver drugs right to a tumor or no other place in the body.
Microbubbles, they are very tiny particles, micron size, and instead of being filled with liquid, they're filled with gas. And because of that, they're visible on ultrasound, and they're used to improve ultrasound diagnostics. So I'm focusing on trying to incorporate drugs into these microbubbles. If I have those microbubbles loaded with drugs, I can inject them into the body. They will distribute everywhere. But then I can disrupt the microbubbles by an ultrasound beam, and the drug will be delivered specifically where the drug is needed. And so this is the exciting engineering design that I'm working on.
It's not just research that stays on the bench. It's research that goes to the market, goes to help people.
We try to dream up things that we feel can really have a big impact, like maybe a super Band-Aid. We set it up to look very much like a gecko because the gecko has enormous adhesivity on their feet, so to speak, and the Band-Aid has all these nano protrusions from it. So there's enormous surface area, and so now we're looking at it for making certain forms of surgery easier, like intestinal surgery, various different types of medical adhesive applications. A lot of times what we do is we license things to companies, or a lot of times we've started companies that create products.
There is other cases in which companies are actually coming in and they're asking us to either assess their technology or redesign their technology.
So we get to see cutting edge technologies, the prototype devices. Major focus of our research is the electrical properties of both skeletal and cardiac muscle. One of the things that we're doing is really novel is we're actually reanimating human hearts. And these are hearts that have been deemed non-viable for transplantation, that were gifts from the organ donors and their families to the lab.
And if they have good enough function, we'll reanimate them and we'll be able to look at the internal anatomy while the isolated heart is functioning.
And just like a heart transplant, you have 4 to 6 hours before you need to reanimate that heart. We'll get it to beat on its own in a native rhythm. And then we can put cameras inside and visualize any of the functional anatomy, really study this device tissue interface of new pacing systems or leads. We actually have a whole free access website that anybody can go online and see the functional anatomy from these human hearts.
Being able to make like an artificial tissue or organ to help someone you love, I mean, that's compelling to anyone, right?
I've been reanimating hearts for the last 14 years, and it's still exciting.
The medical device industry is a consistently booming field. I feel that my job prospects are very good in it.
A large percentage of biomedical engineers actually apply to medical school and go into the health career paths.
I hope to one day be a physician who can kind of be involved in device design and startup entrepreneurial endeavors.
Well, it's a career that just opens all kinds of doors to you.
I think the most important thing as a young student is to get involved early and get involved often. Find research that interests you, because then you'll never work.
Do rotations in different labs at your school to get a feel of what's out there and what would interest you the most.
When I arrived at Minnesota, I looked at 5 or 6 different laboratories and made the decision based on the people working there and the kind of careers the people that graduated from that lab went to.
I started a couple weeks after I became a freshman in college, and it's really paid off for me.
It's essential to know chemistry, to know basic physics, to know basic engineering principles.
The timelines involved here are much longer than in other fields, and that you have to be realistic about that sort of thing.
You have to be passionate about what you do. You have to love your research. When this happens, then you can achieve brilliant results.
I initially joined the Engineering, Medicine, Biology Society to be able to connect with other like-minded people.
That's where I feel that I learned what exciting science is going on in the field.
For a student, an organization like this allows you to connect with people who are well established in their careers, people who can serve as mentors for you as you're developing your career. And more than that, actually get involved with what they're doing.
If you like science, if you like engineering, and if you like medicine, this is just the perfect degree because it combines everything.
If you're passionate about helping people, there's so much to be done as an engineer.
All right, so sorry, Amaya, for taking a bit longer than I was given. That's basically all that I have to say. More information can be found at www.embs.org and many other sublinks. And thank you for giving the opportunity.
Thank you very much, Dr. Wan. We would especially like to remind our gold partner, IEEE EMBS chapter, for the immense support provided to us.
All right. Without further ado, let's take a quick glance of what this workshop series is all about. How can you all get the full benefit of this workshop series? To elaborate the purpose of this workshop series, now I would like to invite the co-chair of Y2NPro, Mr. Ashan Imanta. Mr. Ashan, over to you.
Thank you, Ms. Amaya and Ms. Isuri. Very good evening, ladies and gentlemen. The newest addition to the IEEE Young Professionals Sri Lanka's project fleet will start soon. Before going into details, let me deliver a brief insight into the project structure and the pathway of the inaugural workshop. The Young to Niche Professionals, or Y2NPro project, aims to conduct a series of short courses conveying in-depth and specific knowledge and technical knowledge that cannot be delivered through a regular presentations. Regarding this, the program lead, Mr. Eroshan, elaborated a little bit in detail, so I'm not going to elaborate that more than this. The inaugural project is titled Introduction to BME, is a workshop series designed to teach about magnetic resonance imaging, or MRI. The course content is developed to cover starting from the fundamentals of MRI to industrial practices and troubleshooting techniques. Further insight will be delivered on future development of MRI at the latter part of the course. All the lectures will be conducted by an elite panel of resource persons from academia and industry. An evaluation will be conducted by the resource person at the end of each session. A certificate of completion will be issued for the participant, and active participation in sessions and evaluation is a must. As you can see in the screen, the pathway and tentative schedules are as follows. So today we are going to have the orientation session, which will deliver a comprehensive knowledge about fundamentals of the medical imaging. Our hosts will introduce our very first resource person in a moment, so I'm not going to take that part. After that, starting from 8th January, the workshop series is going to conduct starting from the fundamentals, and in the next week, the industrial applications, and week after that, the future of MRI. Since the program organizing committee, we are aimed to deliver this workshop series as a classroom experience, the participation will be limited to a certain number. Therefore, a registration form will be circulated at the end of today's session. The ExCom of IEEE Young Professionals Sri Lanka will screen the registered participants, and the most suitable participants will be awarded the seats for the workshop series. Hence, I encourage you all to apply for the workshop series at your earliest. Lastly, I must state that the inaugural Y2NPro project is yet to begin, and we are anticipated to develop this into the next level. Therefore, on behalf of Y2NPro organizing committee, I humbly request from all of you to give your comments and feedback regarding today's session. Without taking much time, now I hand over the virtual platform back to Ms. Amaya and Ms. Isuri to move ahead with today's proceeding, while encouraging all to grab the maximum out of today's session. Thank you.
Thank you, Mr. Ashan, for that wonderful introduction. Next up, we have the most awaited session of today's program, the orientation session on It's All About BME workshop series. For that, I would like to invite our guest speaker. He is currently a lecturer at the Biomedical Engineering Program, Department of Electrical, Electronic and Telecommunication Engineering, Faculty of Engineering, General Surgeon Kotelawala Defense University. He earned his Bachelor of Science in Physical Science and Master of Science in Applied Electronics from the University of Colombo. He is one of the founding academic member and was the former coordinator of the Biomedical Engineering program at General Surgeon Kotelawala. Mr. Kanchana, the virtual platform is yours.
Okay. Thank you very much for a nice introduction. And hope you all can hear me. Am I audible to you? Yeah. Okay. So then, can you all
Yes, we are.
see what I am sharing?
Yes.
Okay. Okay. Then, okay, we'll move forward. So, actually, here I'm going to talk to you regarding I mean, give you some understanding or awareness, not actually awareness, just explain what biomedical engineering is, and then what are the areas. Actually, Dr. Ruwan give the first insight. So based on that, I will continue. And if you move further, this is the arrangement I'm going to discuss today. So I'll just little bit discuss on this biomedical engineering, and then how it's different from other engineering fields, and then how we can match this biology with engineering, and then is all only instrumentation, or are there any other fields like that, and then we gradually move into the imaging techniques, medical imaging techniques, and then we'll discuss briefly what are the common imaging techniques used in the field, and at the latter part of the speech, I'll discuss on magnetic resonance imaging, MRI, which will be the topic of next 3 sessions. So if you move forward, actually biomedical engineering, as we discussed earlier also, it's a fuse of different fields. It's an interdisciplinary field. That means simply we use engineering knowledge, not only the engineering, actually engineering based on fundamental sciences like physics, chemistry, in order to give solutions for medical and biological applications. So as Dr. Ruwan said, that engineers are actually developed to give solutions for the problem. So here in biomedical engineers, we are trying to give solutions for medical and biological problems. So that's why we call it's fuse. We fuse engineering, physical science, biology into medicine, and try to design, develop equipment or devices. Sometimes it may be a computer system, whatever, which will be applicable in healthcare sector. So if you move forward, then we'll try to understand why this biomedical engineering is different from other engineering fields. So it because actually we are as a biomedical engineer, whatever thing that we develop, whatever thing we design, we are applied on humans. That means simply it is influence to the human healthcare and the quality of life. So in that case, biomedical engineer is more responsible, should be a more responsible person in case of designing and practicing its profession, because it's directly affected to the human health and the quality of life at large to the society. So in order to developing these applications, in the other thing, all these, whatever the equipment or device or techniques that you design, develop, they are apply on living tissues. That means we can't switch off your body and do the surgery, or we can't actually switch off your body and do any maintenance like that. Okay, so that means we are going to maintain or do the repair, maintenance, surgeries, those things on a working machine. Okay, so that means we have to be more accurate, precise, and it's actually cost sometimes maybe a human life. So that's why it's different from other engineering field, and it's more responsible. And not only that, biomedical engineers are actually trained to work with different other professions. Like for example, he has to deal with consultants, he has to deal with other allied health people like nurses, physiotherapists, radiologists, like that, and pharmacists, because all these areas, there are instruments, there are engineering applications. So that means biomedical engineers should be there. So that means he should be a good team leader and good team worker, and then he need to understand their philosophy, like, because in the engineering we think a little bit different than medicine, like that. So that philosophy, thinking philosophy, pattern little bit different, so then we have to adjust with that. So it's quite challenging. Okay, so and at the nutshell, the knowledge of electrical, electronic, mechanical, physics, like that, all basic sciences and the applied sciences, like all engineering fields, we fuse into develop the application. And in that case, we have to deal with all these other professionals. So that's why another difference, I mean, major difference from other engineering fields. So if we move forward, then I'll would like to invite you to think a little bit different on your body, because actually when I was starting lecturing and then teaching these modules, actually I was thinking how it's good, how it's the best way to deliver this content into engineering people, because actually as a engineering students, undergraduates or postgraduates, so you used to deal with more mathematics and then like that, but you are a little bit away from biology. So that will be some sort of a that means some sort of a negative point sometimes have you in your mind, because how we tackle the biology part, which include in this biomedical engineering. But actually by looking at in different angle as a engineers, so we can look at our body as a machine. So that is the best way of think about it. So in that way, it's very easy to understand all these things. So these processes we did discuss in physiology. So physiology gives you the understanding about these processes, how this process, and then how these controls happen, like that. And then other things also we can look at as a machine. So while you are starting looking at those, and in your body as a machine, then you can find that the most complex machine in the world is your body. Okay. So it has highly sophisticated, computer, So it is really fast, and then fine constructed one. So that control the most of the motor functions and most of the functions in the body. And then it has a very good pumping system, and then it efficiently supply all fluids, energy, and then waste all over the body. And then it has very efficient chemical factory which convert this energy into a some sort of a consumable format, and then use in the cells in the metabolism, so like that. So and then waste disposal plant is also really good and working for more than 50-60 years without any maintenance. So, and then it has more advanced control systems because for example, the control system knows that when you need to have insulin in your blood, and then when the glucose level increases like that, and then the lungs will know the breathing rate according to the oxygen requirement of the body, like that. All these control systems working in there. So that means the things that you learn in your engineering curriculum is there in your body. So only thing that you want to adjust is that just try to understand what's going on there in the human body. That means simply understand the physiology, and then you try to map it with things that you learn in direct hard engineering. Okay. So I forgot to tell that our body has the fast communication system, so it's really quick. And then motor functions is our motors which control our body, upper limb, lower limb, hands, legs, motions, really accurate. So that means the most complex machine in the world is your body. So as an engineer, you will be able to develop things and then deal with this complex body, so without much trouble. So I would like to share a presentation with you. So can you all hear the sound?
Not yet, Mr. Kanchana.
Okay, now I think okay.
Yeah, now it is very good. It's very good.
Yeah. Okay, now here here you can see you have a camera, and then it take the images and then the process it to your brain like that, so you can think on. So this is how we can interpret these lungs. And this is the two-chamber pump we have in our body, heart, which pump blood into the lungs and the body. So here it's represent, I mean, show you that how the digestive system work, and then how the chemical used to extract these nutritions from the foods. This is where that our chemical factory works, and then it stored this energy as ATP, and then store as fat, and then consume required energy, glucose, those things for the day-to-day activities like that. Okay, so then I think you have now you get some idea that how we can move into biomedical engineering with engineering perspective, because actually it's not something what difficult to do, because you have some idea about these processes, those things. So since we have physiology and the anatomy in order to explain the things in the human body, you can map it with the knowledge that you already gave. So in that way, I invite you to study biomedical engineering, so it will be more interesting and much easier. So before moving forward, I would like to little bit discuss about the medical science, because this is the other major part that we are dealing with. The one thing is engineering and the basic sciences. So other part is medical science and the biology. So in this case, actually, the medical science is branch of science. The branch of science that basically deal with diagnosis, treatment, and prevention. That means detection of some sort of abnormality, and then do decide what we do for that, the treatment, and then the prevention, in order to before getting that abnormality or the change, what we can do in this disease. So in this case, all these diagnosis, treatment, and prevention, everywhere instruments, devices will play a key role, because in Western medicine, actually I'm not discussing about indigenous or Ayurvedic medicine, but in Western medicine, so it's always instruments, devices are there to assist physicians in order to take the decisions and then practice these treatments, clinical procedures, and preventions. So in that case, we can categorize into different areas, like diagnostic equipment, like we use to diagnose the disease. So basically medical imaging device like ultrasound, MRI, CT, PET, X-ray, like that. And then the monitoring equipment, so we keep monitoring the patient's parameters, physiological parameters. I'll little bit elaborate it. That means physiological parameters means blood pressure, maybe body temperature, or sometimes maybe ECG. That means electrical conduction and electrical signals which generate in your heart in order to control the physiology of the heart. And EEG, like that. There are many vital parameters which affected SpO2, oxygen saturation level of the blood, like that. So in that case, the medical sciences identify what are the vital parameters need to be monitored, and then engineers can develop instrument in order to do so. So that nice match will help to improve the quality of life. So in monitoring equipment, there's a patient monitors, ECG machines, EEG, blood pressure machines, like that. And therapeutic equipments, they are in order to perform these clinical procedures like surgical instruments, pacemaker, defibrillator, in order to activate the heart, and then dental equipments like that. There are many. And not only that, there are another part, that means if something goes wrong, sometimes maybe some sort of fail to working properly, functionality issue like that, sometimes your part of your body maybe need to be replaced, or sometimes maybe need some assistance. So in that case, biomedical engineers are there to develop implants, prosthetics, and orthotics. So implants, which we put it in your body, and the prosthetics is something that in term of the part of organ or part of the organ, we can replace the prosthetics and orthotics which we wear outside your body. So in that way, there are a wide range of applications all over the field of medical science, medicine, which need instruments, devices. So in order to develop those things, engineers need to be there. So that's why biomedical engineering field this much important in the world, because it holds some sort of a control over most of the industries, because it's really important in human life, because health is the most important thing for person. So that's why, so it becomes key and important in the society. So by looking at these things, you may think this biomedical engineering all about instruments. Actually, it's not like that. So there are many more, because instrument just only not do the things. So there are some softwares, software-based applications, and then some other things that it's not only electronics, electrical, and instrumentation. There are many more. Okay. So according to this IEEE, they have issued carrier guide. So I'll extract, I have extract these areas, the key areas from that document. So they clearly indicate these practical applications. Practical applications means if you are a biomedical engineer, you are in practice. If you like to working in practical with the practical applications, so you can be a clinical engineer or rehabilitation engineer. So clinical engineer is the one who working in hospital environment, responsible for all instruments and devices which use in clinical practices. And the rehabilitation engineering, as in the previous one, that the presentation that displayed by Dr. Ruan, you can see that there are so many applications in rehabilitation engineering, because with this aging population and then some other accidents, increase in the number of accidents, those things. So rehabilitation engineering become key in Sri Lanka also. So basically, those are key two areas which you can working in as a practical biomedical engineer. And then starting from physiology. So physiology explains you how the body functions. So with that understanding, you can study on neural system and cardiovascular system, cardiac bioengineering, and physiological system modeling. Actually, it's really important, because you can, as you as a engineering undergraduate, I think you all have studied about the controls. So here it's nice area, very interesting. Then you can study the same mechanical or electrical control systems. Using that knowledge, you can understand how these physiological control systems working, and then how their feedbacks, and then how these feedback signals work like that. It's really interesting. And then this is what the commonly in Sri Lanka, electronics, technology, and instrumentation, because since now we are really new in this biomedical engineering field, so we need to improve our industry in Sri Lanka. So currently, we are more focused on these instruments, sensors, measurements, and biosignal processing. So medical imaging also you can find easily in Sri Lanka, this imaging processing, radiology, like that. And then molecular biology meets computer. Under that, there are medical health informatics. Nowadays, with this COVID pandemic, people are looking for this type of informatics systems. So then you can communicate your vitals and your medical reports with physicians, and then discuss and get the advice like that. And bioinformatics about the genes, and then gene sequencing like that. And proteomics, that means simply how this proteins are work, and then how infections propagate like that you can study. So then these things highly demanding areas, and then growing areas in the field of biomedical engineering. So we have another set. So medicine meet computers, so information technology. There you can find AI comes into the medical field. So there are many applications in order to assist radiologists in order to identify the tumors, and then these X-rays, this imaging images, whatever the imaging technique that we use, ultrasound or MRI or CT PET, whatever. Then these systems can assist physicians or radiologists to in order to do the analysis. And then the telemedicine is a really growing field, because with these wearable technologies nowadays, it's very common, and then all devices are connected. So simply in this telemedicine, there may be distantly you can operate instruments, and then collect data, analyze it, and then control things like that. So many things, so many interesting things. And then mechanics meet biology. This is area that I really interest, because this biomechanics explain how the mechanical motor functions of your body. And then your gait, you can do the analysis of your gait, and then the motion, and then so many things. But actually the sports field can do so many things with biomechanics. And then not only that, the physiotherapies, there are so many applications. And robotics in surgery, it's also quite new, but it's interesting. So then the material, if you go to this materials, go very small. Under that you can find the biomems. Actually this mechanical engineers little bit worry about this term, because MEMS, it's their own one, but we put bio in front of that, and then we own it, biomems. So that means we are using these MEMS for biological applications in as implant sensors like that, in order to do some monitoring like that. So, and then micro nanotechnology, biomaterials, very key and important part, biomaterial, because all the things that we develop, we are apply on sometimes maybe a living tissue, or in especially implants, prosthetics, or orthotics. So in that case, biomaterials plays a major role. So for example, you can I think you are familiar with these dental applications. So dental implants are there, and then stent. So like that, many things involved and belongs to this biomaterial. So chemical engineering, actually little bit less used in Sri Lanka, but all over the world, it's really emerging, because biotechnology now it's very emerging field. Drug delivery, it's again, sometimes with this nanotechnology, you may be able to develop a system which can deliver drug into that particular point, like cell, up to a cell. and release it, and so then that's called localized drug delivery. Like that, there are many techniques and many technologies emerging in this field. Biofuels is also very much important, and then nowadays the world moving into the biofuels, so it will be a hot topic, hot research topic in future. In the last, biology goes engineering. So there we can find tissue engineering. I think you know what is tissue engineering. That's how we can develop artificial tissues, organs, like that. And then cellular and molecular biomechanics, in order to understand the biomechanics, the processes happen in cellular level, molecular level. And genetic engineering, synthetic biology, so simply that we change the things and develop what we want. So that's what engineering is. That means we are the creators of the world. So that means we little bit change the nature and make it more productive, efficient, and good for living. So biomedical engineering, basically, now you can see it's quite large spectrum. It has very quite large spectrum. So working on, if you are working on electronics, it's there, something's there to deal with in biomedical engineering. If you are working in mechanical, so then again something there to working in biomedical engineering. If you are doing in something in mechatronics, yeah, it's there. So like that, it's really interdisciplinary field. So though what now you are doing, you can, if you are interested in combining this knowledge with biology and medicine, this is the field, and then you need to explore a little bit more in order to working on it. So this workshop series will help you to have a good initiation. So we will move a little bit further, because since now our workshop series, this webinar series focus on imaging, so I will now little bit move into the imaging. So actually in this medical imaging, medical image processing means that we use some sort of a method, instruments, and some we understanding about physics in order to look at it, your body. I will explain a little bit more in detail later. So there we use X-rays, ultrasound, then MRI, magnetic resonance imaging, and then computerized tomography, CT, nuclear medicine, like that. There are many applications. Okay, so actually this method we use to see inside the human body. Okay, so that's what the beauty of this medical imaging. I will explain a little bit more in detail in a few minutes later. So radiology, it's a branch of this imaging. So simply we use radioactive substance, like some sort of ionized radiation, X-ray and magnetic field, like and then the nuclear radioactive material, in order to look at the body functions and processing, physiology of the organs, and then all together we call biomedical imaging and signals. So then actually this medical imaging, as we little bit discussed in previous slide, it simply give you some another dimension. Okay, so that means without opening the body, these instruments, medical imaging, allow you to see inside the body without open it, look into the body. Okay, so in order to explain and then get the understanding about this phenomena, I would like to pay your attention into a different thing. That means if you think, just imagine if you are in 2D world. Okay, so if you are in 2D world, then what are things that you can see? Okay, let's see.
Wake up to something bizarre. All you can see is lines. There's no height, no up or down. You try to move your head. You can't see feet below you or a ceiling above you. Your view is limited to left and right. You try to jump. No luck. You can move, but only forward, backward, left, and right. You check out your room. There are no windows. Just a line blocking you from going anywhere. The wall. You head to the left and right. You finally find the door, a brown line you can push open. If you could float up and look down at your new world, you'd see it. It's as if a thin pane of glass.
Okay, now that means if you are in 2D world, it's only the surface. There's only the area. There's no any thickness. So it's 2-dimensional. Okay. So if you are 2D creature, then if you need to look inside of a closed surface, then let's see what will happen.
Wake up to.
So this is the closed surface. Here is you as a 2D man. Then though you turn around, you can't see inside. You can't see inside. In order to see inside of the this closed circle, you need to open it. If you open it, then you can see what's there inside. But if you add another dimension, that means other than your 2D man, if you become a 3D man, then you can look inside. That's what this medical imaging does. It adds another dimension. So that means it allows you to see inside your body, because now we are in 3D world. So our body is a closed object. So you can't look inside the body without opening it, but you have to do it. So in order to do so, medical imaging helps you. That means it gives you another dimension without open the body. It allows you to see inside it. Okay, that's what the beauty of medical imaging. So that means now once you the pioneer in this medical imaging and the radiologists, those are the gods. That means they can see inside without open it. Okay, so how they do it? So actually they use waves. So there may be a mechanical or electromagnetic waves. So those waves can penetrate through your body, and then there are maybe absorption, reflection, like that. Those are all physical phenomena which explain using physics theories. So using those theories, we are able to construct the morphology or special features of the body or tissues. It may be hard tissue or soft tissue, whatever. So in that way, these waves help us to become God. That means these waves help us to add another dimension. So in medical imaging, we use these ultrasounds, X-rays, gamma rays in order to see or look inside your body without opening. So we will little bit elaborate on these techniques. So the first, the most common and then simple one is ultrasonic imaging systems. Actually, it's mechanical signal, non-invasive. That means you no need to open it or cut it to your body. So non-ionizing, because this is a mechanical wave, it will not ionize your DNA or your tissues, and but its ability to distinguish the interfaces between soft tissues. So that's why we use ultrasound signals in order to look in the your body, look into your body. Okay, so actually it's externally applied, non-tumoric, and then safe at the acoustic intensity. So then that means it's really not harmful. Okay, so there are so many things that we can see in your body using this diagnostic ultrasound. Okay, so we can see your kidney, liver, pancreas, bladder, blood vessels, and then fetus during the pregnancy. I think most pregnant mothers really love to see your baby before the pregnancy. It's really amazing, because in very old days you are just imagine how he is, how she is, or whether it's a boy or girl. Now there's no any curiosity. Now we have opened the sac. So that means you can go into the body and see is there any problem, and then whether whether it's fetus is I mean a girl or boy, like that. It's moreover not much I mean curious secret thing. Then after at that specific dates, weeks, you can see what's how going on there. And then not only that, these breast, eyes, thyroid gland, so many parts you can see using these diagnostic ultrasounds. And then actually these diagnostic ultrasounds, these are on just we not just only look into the body, and then we just get the reflection. So they're using low power levels, and then in that case we use there are two modalities: continuous waves or pulsed wave mode. So continuous waves we use in this fatal heart detector, and then the blood flow like that in those instruments. But in pulse wave method we use in this echocardiograph, ultrasonic scanners, and like that. So in this pulse echo techniques, we transmit a train of short duration ultrasonic pulses into the body, and then we detecting the energy reflected by the surface or boundary separating two media. So actually there we get this physical phenomena, like we call it specific acoustic impedance. So that's where that physics involved in this imaging. So that means simply we use physics theory, and we develop the machines using electronics and electrical technologies, and then we use it. So the presence of discontinuity. So then we can observe if we have if we know the velocity of the ultrasound, then we can exactly locate the position also. So at that level we can do the scanning. So that's why that is the marvel of this thing. And there are another set of ultrasound we use. We call it therapeutic. Actually it's not imaging. I'll just put here in order to give you some idea. So therapeutic ultrasounds we operate with high ultrasonic power, and then there we try to develop some thermal energy there. So if there's any tissue elements, so then in that case we use these devices in order to treat for that type of muscle pains like that. So now you can see this simple mechanical wave can do really important thing. That means simply without opening your body, it will allow you to see the inside of your body. So then we little bit moving into ionizing radiation, X-rays. In your advanced level physics, I think you can remember this is a high energy wave photon. So it can penetrate through soft tissues, and then the absorption levels are different. So in that case we can diagnose some anatomical structure and differences in your organs. Okay, so simply in this X-rays are working there from the very simple chest radiography to digital subtraction angiography. That means some sort of surgical procedures that we use, like we are placing a stent in your heart valve like that, and then computer tomography like that. All these applications we use this ionizing radiation, X-rays. So there may be some sort of I mean issues with ionizing, but with these techniques, procedures, the knowledge on the physics on these X-rays, we able to minimize the effect. So this is how we do the detection. So you have a X-ray source, and then you have a collimator in order to control the beam. So beam width and those things you can control. And this is the specimen you are placing. So you have tissues, the bone, the heart tissue, air pockets, or some tumor like that. Depending on this material, the absorption will be different. So then that means simply the intensity levels will be different. So from that you will be able to identify whether there's a tumor like that. Something abnormal shows the difference of this with the normal. So that difference we use to identify the abnormalities. Okay? That's what we do in all these imaging techniques. So then I will move into computer tomography. That means X-rays. In X-rays, there's some drawbacks. That means simply we superimpose this three-dimensional information into one single plane. So actually it makes confusion in diagnosis. Actually there may be some issues. And again, there's a for the heart tissues, like some sort of a orthopedic applications, then it's fine, because we are more or less our key focus is on heart tissues. But if it is soft tissues, then it's very difficult to understand the morphology and the structure, anatomical structure of the organ. So in order to give solution for this, this computer tomography is invented. It's by Huntsfield at the Central Research Laboratory of EMI in UK. So then it becomes commercially available. There are new modalities and many variation advancements. So like that, now it comes to very advanced, sophisticated instrument which gives you many information about your body. So this is what it does. Simply you can see this term, this tomo, it's a Greek word, so it writes a slice or section. Okay, so simply here to do the same, we just observe a section of your body. So you have synchronized aligned X-ray tube, collimator, and the detector. So you can just move there, and depending on the absorption and those things, you can reconstruct the image, okay, and put it into a video monitor or like that. Okay, so simply this is a X-ray, but you do it not only single plane, it's do it three-dimensional. So then we will move into this positron emission tomography. Now we gradually move into the nuclear radiation. So we use chemical nuclear active material into your body and see how it emit. The emissions will be detected. So that's what we call this positron emission tomography. Simply it gives you again the cross-section image. That's why it's the term is tomography there. So demonstrate the biological function and physiology or pathology. Pathology means how the infection, so those things change like that. So in that case, we put radioactive material into a body. So then we place the subject in a this type of gangrene, and then this is a circular type detectors. So it detects the emission. So simply the positron combines with the electron, it emits gamma rays. So those gamma rays travel almost in opposite directions. It's called pair production and pair annihilation. So it's some sort of theory which is there in physics. You don't need to think much on that. Somehow there are gamma rays, and then those gamma rays are produced. So it emits there. So it penetrates to the surrounding tissues, and there it gives you the information on those tissues. Okay, so all these tomographic methods, we use mathematical algorithm in order to compute or reconstruct the image spatial distribution of this radioactivity, and then accordingly we can develop an image. Okay, so this PET is also non inversing regional assessment. It provides the regional assessment. That means a particular region you can detect, especially tumors like that, because they are that it consume much radioactive glucose. They are like that. There are some sort of medical science basics principles also involving in these instruments. So in that way, the combining the knowledge on medical science, physics, and engineering, we able to have some sort of a good high resolution images using this positron emission tomography. Actually, these PETs are combined with most of the cases with CT or MRI. So I think now Sri Lanka, there are PET CT scanners available. So there you can get more information than standalone PET provides. So then we will move into our topic, magnetic resonance imaging. So there are all these earlier cases, we are dealing with radiation. We transmit a wave into a body, and we see what happens, the reflection or absorption like that. In PET, we insert radioactive material into your body and see how the emission is. Okay. But in the beauty of this magnetic resonance imaging, it's not like that. So it's a little bit different. And then it's high resolution. It has a higher resolution capability, and then it can detect the chemical specific imaging, that these chemistry or these compounds and then those things. So then we can distinguish these boundaries like that. So that's why this obtain anatomical information about the human body. The cross section image is there. So and then it can give you any desired direction. Can easily discriminate this good one, that means normal tissues, and disease tissues like that. Okay. So actually it's total evidence of ionizing radiation. As I explained, there's no any ionizing radiation and lack of none of hazards. So and then penetration bone like that. So that means simply it's quite safe method, and really good high resolution precise images can be taken. Okay, that's why this MRI holds really comparatively large sector in this medical imaging, and then it gives you a good idea about the physiology or the functions of the organ. Then let's see how we can do this. So there we use nuclear spin, because actually I'm not going to discuss much basic theories regarding this MRI. During the webinar series, we will be aware about those things. I'll just give you the insight. So this MRI we use in any atom. You know that there are 3 fundamental particles and then more than that there. But we are just only keen on these 3. So then if it is odd numbers, so then there's a magnetic moment and spin. So what we do, we apply external magnetic field in order to change the orientation of this nuclei, because in generally we are magnetically neutral, because these are, as this graph, this diagram, this image explain, describe this as it's aligned into different alignments. So then the net will be 0. But using a strong external magnetic field, we can align all these magnetic moments into a particular or one direction. So then after that, what we do, we provide another signal, we call it radio frequency, RF pulse, in order to disturb these alignment, and then we stop. So we provide the pulse. The pulse means it's there, and then in a certain time period it's not. So during that absence of this radio frequency, these moments, that means these nuclei tend to come back to the original position. There, that means we swing back to the original alignment. In that change will provide you with induced in MRI, that means NMR, nuclear magnet resonance signal in a coil. That's what we are acquiring and do the processing using mathematical algorithms and produce image. Okay, so that's why we call it magnetic resonance, that means nuclear magnetic resonance, NMR. So we exactly provide this external radio frequency, that means excitation, we call it excitation frequency, external magnetic pulse, radio frequency pulse. So that is exactly with the same frequency of angular frequency of the nuclei. So in that way we can with the external magnetic field we change the alignment, and then we take all these into one direction, and from the radio frequency we change the direction, and with the absence of that radio frequency, it will, these molecules, these nuclei will tend to come to the original position. There it induces this NMR signal. Now you can understand we are not providing any external thing into the body. We just provide external magnetic field and radio frequency which are analyzed. So we use the dipole moment or magnetic moment in the nuclei in your body. So basically most of the fatty water based molecules are response to this signal magnetic field, and in that way we can detect. So this is the this gives you the overall idea, the process that we do in this NMR spectroscopy. You can see this is high energy level, low energy level. So then depending on the this compound, this magnetic moment, it's a vector. So that means we have two perpendicular components. So these magnetic fields tend to align this moment into one direction, and then you have radio frequency radiated at the approximate frequency which is equal to the resonance frequency of this dipole moment, and then with the absence of that it will give you like that free induction decay. That means once you remove it, it will swing back to the original and it will give you NMR spectrum. So now I think it's 100% clear that we are not giving any external radiation into a body or something into body. We use dipole moment in the body in order to develop this image. So that's why we call this NMR images are essentially map the distribution density of the hydrogen nuclei. That's why I call that the dipole moment. Most probably it's related to the hydrogen nuclei. So this parameter reflect in their motion, cellular water and the lipids are the most responsible parts in your body in order to develop help to do this thing. So in conventional X-ray scanner, so it's actually produce a right angle image, right angle to the axis. But in this MRI scanner, actually, see, that means we just excited the nuclei and then we get the induction. So that means by changing the direction, we can get any desired cross section of your body. So that is the marvel of this MRI. So that means you can go into each and every detail what you prefer. So you can see exactly what's going on in your body using MRI imaging. That's why it plays quite important role in imaging. So most of the cases in this tumor detection or some sort of paralysis at the blood clotting, those things we can detect using MRI, because in this reason, that means we can get any desired cross section. Okay. You can see in these images, this is a lung MRI image of a lung, this whole body, and here this is the brain. So like that. So any cross section, if you preferred, according to your diagnosis, so you can get it using MRI imaging. So at last, so now it's almost closer to 1 hour. So though this is very complex machine, I can just summarize this into a very simple 5 steps, this MRI examination. So that means we just put a patient in a magnet. Magnet can be a permanent magnet or electromagnet. So in future webinar series, you may know about more detail about these magnets, and then how strong it is, and then how we can develop that type of strong magnetic field. Like that, there are so many engineering concepts involved there. So it's really a complex machine. So then that's it. So you can understand it in next webinar series. So then what we do, we just have a radio wave, we send it, and we turn off the radio wave, and then patient emits signal, we receive it, acquire it, and reconstruct the picture. That's all. Okay. But in these simple 5 steps, there are more engineering, physics concepts involved in there, and then so many computer based applications, mathematics in order to reconstruct the image, like that. So many advanced technologies involved. So it's so many avenues there in order to explore, improve, and then in the maintenance, and then some other cases, there are so many things to know. So we can spend hours and hours discuss and these applications and these future, those things regarding this MRI. So that's why we have this series. So if you actually, we are invite you to explore more on this MRI, we are by joining this workshop series, and that's all I have to present. So thank you very much for your attention. Thank you.
Thank you very much, Mr. Kanchana, for the knowledge and expertise you shared, and also for sparing your valuable time in joining us today. Mr. Kanchana, please accept this digital token of appreciation from us.
Thank you very much.
Okay, this is the participants. We'll check whether you all have listened to the whole orientation session carefully. This is the time for the quiz. Let me share the screen. All right. So using any device, you all can log into this joinmyquiz.com. Then you can enter this passcode. Isuri, it's already there in the chat, right?
Yeah.
All right.
Ready.
Yeah. All right. Let's go ahead. Still, we do not have anybody. Okay. Hurry up. Any more? Shall we start then? All right, you are getting more. We have 18 participants. Are we good to go? Do we have more? Is that all? Okay. Let's start then. Okay, 1, 2, 3. Let's start. So there are 8 questions and you will be getting 10 minutes to do those questions. Let's go to the leaderboard and see. Okay, Isha is leading. Next we have Dev. All right, it changed. We are having more correct responses than incorrect ones. Let's check. Yeah. Now we have 24 players playing the game. Okay, 40 now already done with the quiz. Okay, we'll wait for 1 minute. All right. Okay, I'm going to end this now. Okay, done. Okay. Let's see who's the winner. All right, Isha is the first place. Okay, this is the scoreboard. Isha, next we have AD. Next we have Vidarshi. Congratulations all the winners. Okay, thank you very much for participating this quiz.
Every good thing comes to an end. We are now approaching the last few minutes of today's program. To deliver the vote of thanks, I would like to welcome the co-chair of Y2NPro, Ms. Kaumadi Kunatilaka. Over to you, Ms. Kaumadi.
Thank you, Izuri. Good evening, ladies and gentlemen. On behalf of IEEE Young Professionals Sri Lanka, Y2NPro Project Organizing Committee, it would be an honor to me to deliver the word of thanks on this orientation session. Y2NPro is a new initiative of IEEE Young Professionals Sri Lanka that will target providing the needed expertise and knowledge to niche communities in various industries. The first program of Y2NPro is this series of workshops on magnetic resonance imaging, MRI, in biomedical engineering. Today, we have come to the conclusion of the orientation session of the MRI workshop series. I hope you all had a very informative, funny evening today, since you have met a bunch of people interested in biomedical engineering. We would like to give you all a big close of approval. And thank you all for the registering and participating in this orientation. You all are our biggest strength. But the workshop is not yet over. Please wait for the next registration to open. I would like to express our sincere gratitude to the guest speaker of our event, Mr. Kanchana Wijesinghe. Mr. Kanchana, thank you for accepting our invitation and spending this special moment with us. Next, our gold partner, IEEE EMBS Technical Chapter. Thank you, EMBS Global and Sri Lanka chapters, for the immense support that you are providing throughout this workshop series. We are inviting IEEE EMB Society to always be with IEEE Young Professionals Sri Lanka. I would like to express our sincere gratitude to Dr. Y2NPro for making us aware of EMBS on behalf of IEEE EMBS Sri Lanka chapter. If any of you wants to join EMBS, you can simply ask questions on that WhatsApp chat. I think everyone is in WhatsApp chat, right? Dr. Y will support you to collaborate with EMB. Let us advance medicine and biology through the application of engineering, sciences, and technology. We, IEEE Young Professionals Sri Lanka, is driving through the mission of increasing the industry members' involvement in the organization and enhancing the recognition of the organization among the industries to attract and benefit fresh graduates. Our executive committee is our biggest strength. Thank you, YP Executive Committee, for your immense support to make our project reliable. Teamwork makes the dream work. We had a dream. We made it reliable. Y2NPro Organizing Committee, your co-chair is always proud of you. Thank you for the sleepless nights and patience towards our project. Finally, I would like to thank all the individuals who supported us directly and indirectly to make our project a reliable, successful one. Thank you. Over to you, Amaya.
Thank you, Ms. Kaumadi. Isuri, what are your feelings about this session?
It was awesome. I had a very informative evening today, especially hosting with you.
Me too. Let's ask the audience how they felt about this orientation program. So for that, we will be sharing and emailing the feedback form, and I think it's already there in the chat box as well. Please feel free to give us your comments and suggestions for our program. And also do not forget to join our WhatsApp group. If you have any questions related to today's program, you can ask them through WhatsApp. Our speaker is already there, joined in the WhatsApp chat. So join-in link is already there in the Zoom chat.
Before winding up this event, I kindly request the audience to switch on your cameras to take a group photo according to this new norm.
Take the photo, please turn on your cameras. And this may take a little while since we have a couple of participants. So on my count, we'll wait a few more minutes. Please turn on your cameras. Okay, on my count, say cheese. 1, 2, 3. Say cheese. One more to go. Okay, say cheese. 1, 2, 3. Right, all done. Thank you.
With that being said, we can conclude today's proceedings. We are IEEE Young Professionals Sri Lanka. Don't forget to follow up on Facebook, LinkedIn, and YouTube. Thank you for your wonderful participation.
Have a good day and stay safe until we meet again. Thank you.